For this video, I'd like to discuss how to graph logarithmic functions. And you can see I've started with this parent function, y is equal to log base 2 of x, which is essentially the simplest logarithmic function we can have. And we want to get a picture of what this equation looks like. So before we do that, if you're not sure how to draw a picture, you can always fall back to drawing a table. So essentially, given specific x values, what is y equal to? And let's start with x equals 0. So let me make a little bit of room here. So for x is equal to 0, we have y is equal to log base 2 of 0. So this is 2 to what power gives you 0? Or in other words, we could rewrite it as 2 to the y equals 0. And the truth is, there is no exponent that we can raise 2 to get a value of 0. Recall the exponential function, y equals 2 to the x. If we were to quickly graph that, it looks something like this. It's a sloppy picture, but you get the idea, where essentially there's an asymptote at this line y equals 0, or the function never crosses this line. So looking at our particular function here, this logarithm just doesn't exist when x is equal to 0. So we can write does not exist when x is 0. And in fact, what we're going to see is that x equals 0, this y-axis, is essentially going to be an asymptote for us. But before we get to that point, let's start plotting some other values. So when x is 1, let's see what y would be. So this would be y is equal to log base 2 of 1. So 2 to what power gives you 1, and 2 raised to the 0 power gives you a value of 1. So we know this graph crosses at the point 1, 0, so that's this right here. And now we're going to plot some other points. So let's try 2 for x. Then we have y is equal to log base 2 of 2. So 2 to what power gives you 2, and that would be a value of 1. So we also have the point 2, 1, so right there. And I'm going to pick some specific values that essentially make the logarithm evaluate to clean numbers. So let's say 4 for x, and we have log base 2 of 4. So 2 to what power gives you 4, and that would be a value of 2. So the point 4, 2 is part of the graph, and I'm also going to choose an x value of 8. And what you'll see is that essentially 2 to what power gives you 8, and that would be to the 3rd power. So we can also graph the point 8, 3, which would be somewhere over here, let's say right there. And we can also get an idea of what happens between 0 and 1 for the x values. So in other words, what if we looked at an x value of 1/2? So this becomes y is equal to log base 2 of 1/2. So 2 to what power gives you 1/2? And that would be 2 to the minus 1 power. So let me extend that just a little bit and try and separate these a little bit. So we got 1/2 for x and a y value of -1. So that'd be right there. And we can continue this. If we look at an x value of 1/4, then what you'll see is that the y value would be -2. Since 2 to what power gives you 1/4, and that would be 2 to the -2 power. So we can graph that point. So 1/4 and -2, that's right there. And you'll see if you did 1/8, that would be at -3, and you can keep going. But essentially what you'll find is that you have an asymptote at x equals 0. So let me write that down. This is an asymptote. So the function will never cross this line. So let me now sketch this picture. And with that, we've now completed a relatively accurate drawing of this equation, y is equal to log base 2 of x. And what you can notice is that if we compare this to its inverse function, y is equal to 2 to the x, that they are mere reflections about the line y is equal to x, since that is essentially the property of inverse functions. So if we drew this one, I'll just draw it real quick, not too neatly, but you get an idea. So you can see that these two functions, the logarithm and the exponential function, 2 to the x, these are inverse functions, and they do exhibit this property where they are symmetric about this line y is equal to x. So with that in mind, with the basic idea of graphing these logarithms and essentially just making a table and evaluating the logarithm at different x values, let's look at more general logarithmic functions and think about how they're transformed. So let's look at this first example problem here, where we have y is equal to 4 times log base 3 of minus x minus 3. And before we try and consider the transformations, anytime I see a negative attached to x on the input, I like to factor it out. And once you factor it out, it's more clear how the function is shifted left and right. So let me rewrite this. So we now have y is equal to 4 log base 3 of minus x plus 3. And once we write it like this, now it's more clear what all the transformations are going to do. So let's start with this 4. So that's going to stretch by a factor of 4. And then we have on the inside, we have this negative. So that is going to reflect. But since it's on the inside, or essentially it's part of the input, it's going to reflect across the y-axis. So essentially, if you had an x value of 2, you now are dealing with an x value of negative 2. It flips the x values. So this is a reflection about the y-axis. And then we also have that plus 3 on the inside. And I always think which x value makes this expression 0, and that would be minus 3. So that tells us we want to go left 3 units. So to actually graph this, though, now that we have all the transformations, I'm always going to start with my parent function, that y is equal to log base 3 of x. Though we looked at base 2 of x in the previous example, but in all honesty, they look almost the exact same. Their points are just slightly shifted. So if I quickly draw this graph, it looks something like this. And it's got this key point of 1, 0. And what I like to do when trying to graph more complicated logarithms is essentially track what happens to this point 1, 0. Though if you want, you can also find another clean point in this graph and see how that's transformed. So for instance, with an x value of 3, the function should be equal to 1, and you can see I didn't draw this perfectly because it would be down here. But that's another option, looking at where that point moves as we transform this. So with that in mind, we're just going to follow this point 1, 0 and essentially see how it's moved. So I'm going to draw that right there. And so the first thing we do is stretch it by 4. But that's stretching the y values, and the y value is 0 here. So this is actually not going to affect this point right here. But then we have a reflection about the y-axis, so that's this axis here, and it's going to reflect, so it's going to be a mirror image on the other side. So now we just moved it to -1, and then we're shifting everything to the left 3 units. But that also includes shifting the asymptote. Because remember, we started with an asymptote of x equals 0, but now everything's going to shift 3 units over. So since we've already applied the other 2 transformations, the shift of 3 over, this point would actually be a part of the graph. And now I'm going to draw in the asymptote, since it was at x equals 0, but now it's at x equals -3. So let me label that in. We have x is -3 for the asymptote. And what I like to do next is just pick a point nearby that would work cleanly with this function. So in other words, I'm going to pick either this x value, let's see, this would be -5, or an x value of -6. And ideally, when I put this in here, I want to get a multiple of 3, since that would just be easier to evaluate. So I'm going to use an x value of -6 and essentially see what happens to our equation when I plug this in anywhere I see an x. So when I do that, I'll have y is equal to 4 times log base 3, and then I have minus -6, so the negatives cancel, and I have +6 minus 3. So that would just be a 3 on the inside. And remember, this is when x is -6. And when we evaluate this, log base 3 of 3 is just 1. So y here is just equal to 4. And so we can graph that at -6, 4. We now have another point. and our function. And with all of that, we know that the function is going to decrease and essentially hug the asymptote, and then follow essentially the logarithmic curve, which grows very, very slowly. So it's going to curve like this. But if you wanted, you can put in more points. It's just, if you pick an x value of -5, it's just not going to evaluate to a clean value. But if you know how to use the change of base rule for logarithms, you can still do an x value of -5. So let's now look at one final example where we have y is equal to 4 times log base 2 of x plus 6 minus 8. And let's compare this to our parent function, y is equal to log base 2 of x. And what we're going to do is essentially look at what every different transformation did to our parent function. So let's start with this point right here, or this coefficient of 4 on our logarithm. So that just means we're going to stretch all of our y values by a factor of 4. And then let's now look at this plus 6 on the inside. And again, I always just think which x value makes this expression 0. And it would be -6. So that tells us we're going to go left 6 units. And then we also have that -8 on the outside. So this right here, that's just going to shift all the y values down 8 units. So recall from the last example, I like to consider essentially the feature point of this parent function. Remember, it essentially looks something like that, maybe a little bit less steep, but it goes through this point 0, 1, or I'm sorry, 1, 0, and we're going to essentially track what happens to that point. So let me replot that point 1, 0, and now we're just going to follow these transformations. So it's going to stretch by 4, but since the y value is 0, multiplying that by 4 would still keep it at 0. So the stretch doesn't actually affect this point. But then we're going to shift everything to the left 6 units. And recall that our asymptote was on the line x equals 0. But now even the asymptote is shifting left 6 units. So let me draw in that asymptote. It would be at -6. So 2, 3, 4, 5, 6. We'll draw it in right here. And then this point also got shifted 6 units to the left. So that would be right here. And then that point's also going to shift down 8 units. So 1, 2, 3, 4, 5, 6, 7. And I'll draw in an 8th line there. So it'll be right here. Though this point right here, this is actually part of the graph. So I'm going to draw it in that orange color just so that we know this is officially a part of that graph. And now the next step, since I know the asymptote, is to find a value from a point right next to this one. So this is an x value of -5. So I'm going to choose an x value of -4. So when x is -4, we want to figure out what y is equal to. So let me rewrite that. When x is -4, we have y is equal to 4 times log base 2. And then we have -4 plus 6, which is 2, and then -8. And log base 2 of 2 is 1. So this just becomes 4 minus 8, which is -4. So when x is -4, y is also -4. So here is a second point on our graph. And that's really all you need, because now we also have the asymptote and we can combine all of these features. Though if you want, you can also get a more accurate graph by figuring out the y-intercept, plugging in x equals 0 into the function and seeing what you get. So if you plug 0 in here, you're not going to get a very clean number. So I'm not going to actually evaluate that because you'd have to do log base 2 of 6, which is not a whole number. But if you wanted, you could still do that and evaluate it with the calculator. But I'm not going to do that, so my graph's not going to be perfect, but you can at least get a general idea of how it's supposed to go. So that is essentially what the graph would look like.